it's the same link.
Yeah.
You have microphones? Good.
I'll wait for a minute for them to come up.
I think you can.
I'm
not sure. Not sure it's gonna happen.
Okay, it's done. Thank you for inviting me to this talk. I am Bert from, now I'm working in Google in Tokyo. I'm talking about collective co-directedness in collective systems using cell automata as examples. I have a few discussions with Martin about what's agency, what is co-directedness. It seems like a simple way to put it is something, if they are trying to do something, try to do some action, then we can say that it's having some agency. Try is the keyword because maybe it will fail, it will succeed, but at least it's trying. For goal-directedness, it should be like doing something for some belief or some goal. And for agents, to do something, it needs a sensor to check the environment, and then it should have a controller like a brain or to decide what actions to take, and then actuator like a hand or foot to do some actions. And then it will still use the sensor, like the eye, to check the results, and then check against the goal, see if it's achieving the goal, and then do more actions. And some higher level of the controller can predict results and have a better actions. And it's we usually divide two kinds of agency. One is mechanistic, like RL agents or a robotic agent. The agents is quite well defined because we have a sensor, we have actuators, we have a controller, there's a brain. Especially in RL agents, robots is well defined because we need to train the brain with the very the fixed sensors and actuators, and the agent will react with the environment. But in biology and also in cell automata, another view is more common and also more useful, like the activist view. The agents are not always there. They can emerge and they can disappear in any time. And also the constituents, which component will become an individual, it become an agent, is also not very clear. Sometimes is the, especially in cell automata, is the person that's defined, oh, this is an agent. So in this kind of continuous CA, that I will say later, for each component, each of this cell, can you say this cell is a sensor, is an actuator doing some action, or is it a controller, or even is it inside the agent or inside the environment? We cannot say that. And we can even say that, oh, where is the goal sits inside this agent. In many kind of persistent pattern, usually the ultimate goal is survival. In biology, each life form, the goal is survival. I like the saying that life is pattern that want to repeat itself, or the saying that I persist, therefore I exist. Because a pattern that no longer exists, then it will just disappear. But some patterns that they have the capability to keep going on, they will just exist. Yeah. And usually these goals will subdivide into sub-goals like autopoiesis, homeostasis, or like higher forms, they will have connection or some sexual reproduction. So we usually talk about goals in individuals. How about some collectives, like multicellular organism, like social groups, like a conference, a nation, or a social group, or in terms of cell automata, there's some patterns. The goal will, in these collectives, will become the survival of the group, because if it's not surviving, then the group will simply disappear. I'm using cell automata as an example. So in the Conway scheme of life, in the upper part of the diagram, shows that you can say that each cell, individual cell in the Conway scheme of life is actually having a very simple goal. Is for homeostasis. Is sensing the environment around the cell, and is the control is the rule that if there is rule to maintain certain kind of density near the cell, and the action is updating its own value. But once an emergent pattern appear, like this glider, we can say that the goal of the glider is to survive, but it also have a suppose that autopoiesis, it keeps generating cells, on cells in one direction. But this kind of goal directedness or the actions are quite fragile because of the small basin of attraction of the attractor of this kind of action. We can even build cell automata machines that, for example, calculates digits of pi or have some universal computers in Conway scheme of life. The goal is complicated, but it's still very fragile because the attraction for basin doesn't expand. In some other examples of C, like larger than life, they have a larger kernel, so the basin of attraction become larger and the pattern become more robust. In terms of linear, which is a continuous version of cell automata, we can see later that if a feeling that the capacity of having complex goals increased, I don't have a quantitative a method to try to say how high is the capacity, but this is some qualitative feeling. For example, in linear, we can see self-replication or patterns that try to they can survive collisions pretty easily compared to simpler cell automata. And these patterns are pretty robust because maybe the basin of attraction is quite large, and also the types of attractors become, we can have some kind of strange attractors. So to see how high is the capacity of this, can we give some goals to these patterns? We do some experiments. For example, we can try to evolve these patterns using evolution algorithm like CMAES. I was using the EvoJax framework done by Tan et al. In Google. So for example, in the left-hand side, we have a normal pattern in linear. And we try to evolve, for example, can we have patterns go faster or spin faster, or even have a larger variance in mass, so it's like going up and down. And it proved that it's possible to give this optimization task. So we can say that we give this kind of goal instilled in this pattern. after the evolution. So using machine learning, we also with the people from in India, we use neural cell automata and also curriculum learning to train the patterns with a step-by-step goal. And then the step-by-step is first to guarantee the survival of the pattern, and then the pattern can move further and further, and then to avoid some collisions with some obstacles. The patterns can even generalize to unseen obstacles or collisions between the creatures. So once again, it proved that we can give like some kind of obstacle course to survive in this course as a goal of these patterns. The third experiment is trying to use JAX to do some large-scale simulation. The goal is we back to basic, just for the survival of the pattern, and not some extrinsic goal. And in this experiment, we managed to evolve a very open-ended different types of pattern. They have different kind of behavior. And at the end, it's some linear structures with over the space. They are very adapted to this kind of environment. So we can say that even for the very primitive kind of goal, like just survival, also is possible in this linear system. So seeing this linear as an example of we can have goal-directed behavior even in some cell automata. I have some more thoughts, like in certain kind of higher level collectives. I was thinking about this because when I was in Tokyo in my office, I'm looking at the city of Tokyo, which we can say city is a higher level of collective, which is built by human as a component. I asked the question that would a city or like a larger group of humans have its own goal or its own set of sensory inputs or its own actions that we as a component that we don't understand or we won't know, is some kind of philosophical question or even like something supernatural, but it's not totally not happen in the biological world, because I saw a tweet from Sarah Walker that's talking about we only as a biological multicellular organism, we only know about the components, which is the cells, only after we invented microscope. So we, as a higher level organism, we don't even know the existence of the components before 100 years ago. So will some higher level group that exists somewhere in a society or an ant colony, that they won't know the components, which is us, which is humans, and we humans cannot communicate with them like the higher level beings. So it's just some a strange kind of question that we can ask ourselves. So as a components, can we recognize the goals of the collective? Like, can we know what the group wants, or can we help the group, or should we help it? And if the goals of the components of the collective don't align, then what will happen? Like if there's some protests, or like in terms of multicellular animal, like some cancer will happen. So yeah, there's some more strange thoughts that in this talk I'll talk about this. Thank you.